Hi viewers, this is Sri Ramlu. Today's topic is Faraday's laws of induction, differential form and integral form. Okay, so there are the two different forms, differential and integral forms are there. So first two, Faraday's laws statements. First statements, there are the two laws. So first law and second law are there, and the first law statement is, see here, whenever the magnetic flux linked with a circuit is changed, an induced EMF is produced in the circuit, right? Whenever the magnetic flux linked with the circuit, linking means touching only. Okay, when they touch with the circuit, then what happens? Then induced EMF will be produced in the circuit. So that is the Faraday's first statement. See here, suppose it is one circular coil. Let it is circular coil, and it is one magnet having the north pole and a south pole. Bring this magnet towards it. You know first properties of magnet. So first you must know the properties of magnet. If it is a magnet, bar magnet, north and south pole, and the lines of forces are like this, right? Generated from N and ends with S. Okay. When we move away from these poles, this side, then magnetic field decreases. But when we come towards the north pole, magnetic field increases. Same thing this side also. When we move away from the south pole, field decreases, and when we come towards the pole, south pole, field increases. So that means at the different points, at the different places, magnetic field is also different, right? Now see. So let it is a circular coil. Okay, so what he is saying, circuit, let it is a circuit or circular coil, and bring one bar magnet from long distance towards the coil, and connect the two ends of this coil to the galvanometer. Right here, connect one galvanometer. Okay, so at the beginning, galvanometer shows the reading 0, right? So if it is a galvanometer, and we may find the values like this: 1 this side, 2 this side, 1 2, right? In this manner we may find. But at the beginning, arrow mark shows only 0. But when the current flows, the arrow mark starts deflecting either right side or left side. Okay, depending upon amount of current and direction of the current also. Okay, now see, it is a bar magnet. When it comes towards a coil, then what happens? It has already magnetic lines of forces. When it is coming towards it, magnetic field increases. Okay, so that means magnetic field is changing minimum to maximum. So changed, right? So when magnetic field changes, when links with the circuit, then in this circuit, induced EMF will be produced. That induced EMF can be shown by this galvanometer. So that is a statement of first. Okay, when there is a circuit or circle or coil, then if you bring the bar magnet nearer to it, so bar magnet having the lines of forces, all the lines of forces links with the circuit, and in the circuit, induced EMF will be produced. But if it is a circle, if it is a circuit or if it is a coil, if you bring bar magnet and if you kept here only without changing its position, then you cannot get any change in induced EMF. Induced EMF cannot be produced when bar magnet is stationary. When bar magnet is moving, then field changes. Moving field changes means when it is coming nearer to the circuit, field increases. When it is going away from the circuit, field decreases. So changes are occurring. So when the changes occurs, then only induced EMF will be produced. That is the first statement. Once again see, whenever the magnetic flux linked with the circuit, right, circuit is changed, right? When that field must be changed, then induced EMF is produced in the circuit. All right, so that is the first statement. And the second statement is the magnitude of induced EMF is directly proportional to the negative rate of variation of magnetic flux linked with the circuit. Okay, so here what we said, induced EMF produces. Okay, that produced EMF, how it is, for what it is directly, so that is saying in the second statement. Okay, so second statement definition, its formula. By using this formula also we can say its a definition. So induced EMF is directly proportional to the negative rate d phi by dt. Here time is there, when there is a time then only rate word will come. Okay, so rate of change of flux linked with the circuit, that is this is the second statement of Faraday. And first equation is when there is only one turn. If there are the n number of turns, then this is the formula. Next, integral form. Consider that magnetic field is produced by a stationary magnet or current carrying coil. Suppose there is a closed circuit C of any shape which encloses a surface S in the field as shown in figure. Okay, so what we have to consider, first we have to consider magnetic field produced by a stationary magnet. One magnet we have to take which produce magnetic field, or you can take current carrying coil also. Why? Because when the current passes through the coil, then magnetic field also produces. Okay, so either magnet or current carrying coil also. And now what we have to take in the second statement, second line, what is saying, take a closed circuit and let it is C of any shape is not important, which encloses a surface, that means which has a surface area S, that is the meaning of S, in the field as shown in figure. So see, there is one figure also, and this figure is this one. This figure is what I am saying. So it is any shape, it is a irregular shape. Okay, and these are the lines of forces are coming outside, and here what we have to consider, one small surface. Total surface is S. Okay, total surface area is S, right, and the small surface area is ds. So ds we have taken, and if we integrate, then we can get a total value. Okay, let me go back. Okay, let B be the magnetic flux density in the neighborhood of the circuit. So just now what I have shown, there is a diagram, and just beside it there is a magnetic field, and it is coming outside like this. Just now I have shown in the diagram. The magnetic flux through small area ds will be B dot ds. Okay, so it is a magnetic flux through small area. Why it is? General magnetic flux formula is B dot ds. Okay, so that is why it is written. For the small area only, small flux is present. Now the flux through entire circuit, right? It is through entire circuit. For the small area, flux is d phi is equals to B dot ds. For entire integrate on both sides. Here integration differentiation cancel, you can get here only phi is equals to B dot ds. So this is, let it is equation number 2. When magnetic flux is changed, electric field is induced around the circuit. Okay, when changing flux present, induced EMF will be produced in the coil. Next, the line integral of electric field gives induced EMF in the closed circuit. Okay, so in this closed circuit, how much field is produced, how much EMF is produced? So that EMF is simply what it is, a line integral of electric field only. So line integral is E is, let induced EMF is E is equals to E dot dl, right? So this much of field will be produced, and here dl is what? The small length is taken. So in the small length, if you find the small induced EMF, okay, in the small length, the small induced EMF is d, E dot dl, and if integrate on either side, here differential cancel, E is equals to integral E dot dl. So like this we got equation number 3. See, this is small length is considered here for like a small area. So it is area in between this circuit, and length is on the circuit. Now from it is actually not from Faraday's second law. So we know Faraday's second law, E is equals to minus d phi b by dt. Okay, and phi b term also is given in the equation 1. Okay, phi beta in the equation 2. So what is equation 2? See here, equation 2 is phi b is equals to integral b dot ds. Take that value and substitute here. So this is okay, E is equals to, let it is equation number 5. Now compare 3 and 5. E is also E, so then these two are also equal. These two are equal, then this side also equal. Now see, so from equation 2 and so substituting equation 2 in equation 4, substituted, we got the 5, and from 3 and 5, right, 3 and 5 it is the equation, and write minus dB by dt inside. So then it is differentiate only b value, so minus dB by dt, that becomes this is the what you know equation 6 is called integral form of Faraday's law. Integral E dot dl is equals to integral minus dB by dt dot ds is the integral form of Faraday's law. Next, differential form of Faraday's law, right? So differential form. So if you have to calculate the differential form, we must take the equation 6, that is integral form. So by using this only we can calculate the differential form. Now see, integral E dot dl is equals to integral minus dB by dt dot ds, right? Now by Stokes theorem, so convert this one. Stokes theorem formula is what? E dot dl is what? Del cross A. Generally, if integral A is if it is a vector, dl is equals to what? We can write integral del cross A dot ds, we have to write. So that means simply length is converted into area, and at the place of A, del cross A will come. That is Stokes theorem only. Okay, so it is Stokes theorem. Now this term substitute here, this is okay. So that means what is this, you know, see equation 7 and 8, these are equal, then this side are also equal, that is here. Okay, so this is written this side, it is written this side. Now it is ds and this is also ds. Then in the place of del cross E, what you have? So first to multiply this dy by dt inside. So let d become dou, nothing will happen if you write a d as dou. Okay, now see, in the place of del cross E, so it is also ds, it is also ds. In the place of del cross E, what you have? It is minus dou b by dou t. So del cross E is equals to minus dou b by dou t, or curl E is equals to minus dou b by dou t. E is called differential form of Faraday's law. Okay friends, so this is the differential form, that is either this or this, and integral form is, so equation 6 is, it is integral form. Okay friends, don't forget watching this video, subscribing and sharing to your friends also. Thank you friends.